Okay, I see your point. Yeah. Okay. Good. So I get carried away with my bars, but I know what I mean. As long as I know what I mean. Okay, so this is the initial value problem, and my claim is the following. So if my vector field function f, which is a mapping from Rn now to Rn, is of class C1. Does everybody know what I mean by this thing? When I say a function is of class C1, C0 means continuous, C1 means it has continuous first partial derivative. So whenever you say in math that something is CK continuous, K means that the first K partial derivative are continuous. So for existence and uniqueness of solutions to the dynamical system, all that is required is that your vector value function f be of C1. So all the possible partial derivatives of f be continuous. Yes?
Does this only apply for the multivariable function?
No, you can talk about any function being CK. So even standard one. But because a partial derivative of single variable function is just the ordinary. So it applies. Okay, so the first partial derivative must be continuous. Okay? That's what we mean by C1. So if that is the case, then we can state the following. Then, for all initial points, A, R, N, there exists an interval, which I will just denote as I did before to keep it consistent, minus delta to delta. And a unique function, call it psi, that is mapped from this domain to Rn such that y prime of k is equal to f psi of t. And psi of 0 is equal to a. So in other words, if psi of t is my solution to my initial value problem, it exists from this interval minus delta to delta. So a solution exists and it's unique within this interval. And all that is required to make this statement is that f be C1. Most of the dynamic systems you will see in this course certainly will have this. But it's not always the case. Especially what I do. Nothing is ever C1. Very long. But the point of this is, as before, it's a local result. You only can guarantee existence and uniqueness within some interval. So in this case, it's minus delta to delta. I might as well write it. So this is a local result. It guarantees the existence of a solution in some interval. Minus delta to delta, centered at t equals to 0. So it's almost identical to what I wrote down before when we were doing the standard existence uniqueness for the one-dimensional. Okay. So that's the theorem on existence and uniqueness. So as long as you can get a dynamical system that is C1 continuous on the right-hand side, you can guarantee its solution within some. But then related to this is the following thing. So theorem 2, which is called Maximality. So assume you're given a C1 continuous function f, and therefore there is some finite interval where the solution exists and unique. is there a way I can extend this interval of solution to some maximal point? Hence you get something called a maximality. And that says the following. So, as before, let psi of t, or just psi of t, be the unique solution of x prime is equal to beta of x. So the unique solution of my dynamical system, where I will just state it again, f is C1 continuous, which satisfies my initial condition. So in other words, psi of t here is my solution to my initial value problem again. Then, let me denote, let's say t min to t max as the maximal interval on where psi of t is defined. If t max, which is the right endpoint of this order interval, is finite, then we can say the following, which I will write on. So, if t max is a finite number, then we can say the following. Namely that the limit as t goes to t max of the norm of phi of t is equal to plus infinity. What does this statement mean? It means the following. So meaning, the solution can be extended indefinitely. Unless there is some, as we saw with our example before in the bonus question, some finite time divergence. Finite time divergence. Fine. Any questions about it? So the idea is that even if you have your solution that's existing in some finite interval minus delta to delta, as long as you don't have some blow-up of solutions, you can keep extending this interval indefinitely. But it all crucially depends on f being C1. So it doesn't matter really that it's nonlinear. It just means that it should have continuous first partial derivative. Nonlinearity actually is not a problem. It's when you have some weird functions that have singularities and all these types of things. So then none of these theorems are very helpful, but you do what you could do. So let me now hopefully just restate. Well, I mean, I've talked about flow a lot. I can restate. Any questions about this? Okay. So I've introduced the concept of flow, but related now to the idea of maximality, let me connect how flow relates to this. Because, remember I said, and I'll show you a diagram of this on Wednesday, maybe, from one of the things I did. The idea is that the flow should reconstruct all possible solutions in the future, right? You have a bunch of initial conditions. The flow should dictate what all possible solutions look like in the future. But I asked you this question, if I give you some initial state, because the dynamical system is deterministic, you can tell me what the future state will look like. Right? I asked you this question before. But now the reverse question, if I give you the final state, can you tell me what the initial state of the system is? But, in principle, because these are ordinary differential equations, you should be able to, but it's not always possible to do so. So given some final state, you cannot always reconstruct the initial state. And their flow idea is related to this. So let me write that explicitly. So note, because it should be expected, I mean technically, they're just different ordinary differential equations. They're not partial differential equations. So there's no issue of causality or anything in these systems. It's just ordinary derivatives that have deterministic flows behind them. So there should be technically no problem if you start with the final state for you to tell me what the initial state looked like. But it's actually quite complicated in practice to do that. So related to that is the following. So it may happen that solutions of the dynamical system are extendable for maybe time only going in one direction. So t, let's say, going to positive infinity. But not for t going to minus infinity. So you can talk about a determinism going into the future, but I cannot evolve the system uniquely back. So maybe the flow is only possible with t going to positive infinity, but not backwards, minus infinity. So if this is the case, then one talks about, instead of a flow, you talk about what is called a positive semi-flow. Positive semi-flow. And instead of phi t, we denoted phi t with a little plus sign. So phi subscript t superscript plus sign. And similarly, if it could also happen that you can see some systems that are extendable backwards but are not extendable in the future. So you can start with some final state. I can give you the initial state of the system, but I cannot go beyond what that final state was. Which is very strange, but it happens all the time. So the opposite, it's more rare, but the opposite happens as well. So you can start with some final state. You can uniquely tell me what the initial state was, but then I cannot construct for you what the time looks like in the future. Yes?
Is there some real example?
They're all in cosmology.
Okay.
So you'll have to piece it. So they're all in actually cosmology and relativity theory, but it happens all the time. It will not happen in biology, for example. Their flows are very nice and simple. In cosmology, you get these types of things with singularities and being able to reconstruct the image. So a big problem, for example, is we know right now what our state of our universe is, because we can observe it. Reconstructing the initial state or the Big Bang is a very difficult problem to do, actually. It's directly related.
And reconstructing the forward beat, you can't do that if you don't know the house.
You can construct the future evolution, but not uniquely. There are many different possibilities that can happen. So I'll show you some examples of this still, okay? But yes, just to make you aware that some weird things are possible when you go in the realm of nonlinear physics and nonlinear mathematics. Because now we're being very general. None of this stuff occurred in the linear system scale, right? Okay. So similarly, if solutions are extendable for time going to minus infinity. So when I say time going to minus infinity, I mean going backwards. But not for t going to positive infinity. Then we talk about a negative semi-flow. then we have a negative symbol. And we denoted phi t with a minus. Yes?
Okay, so the last few lectures,
Yes.
you've been like setting up like the structure of why like differential equations, all these things work,
Yes.
and like the background.
Yes.
So as for the exam, will it be something where you'll ask us what?
No, so I have to introduce this machinery now. So for the next 2 weeks, I can do nothing but example.
Okay.
But see, the difference is that, and I don't mean this in a negative comment, the biology way to do this, and the way it's been taught before, is basically saying, ignore all of this. Here's Mathematica, type in your differential equations, and observe the solution. I don't see any work on that for a course like this. So at least this way, when you're confronted now with the general nonlinear system, right now it seems you can't do much with it, but in 1 or 2 more lectures, you'll be able to start doing it by yourself. Picking apart nonlinear equations, telling you a lot of information. So I'm asking you to be patient for like literally 2 more classes.
No.
Then I will start doing examples from biology, from neuroscience, all the stuff I showed you on the first day. Game theory, cosmology, and you'll see it's all the same thing. So at least you'll be able to understand it. That's my goal, my hope. But no, the exam will not be like this, theoretically, with proving things.
It just seems like you're trying to like lay down the foundation.
I have to, because also there's no course in the undergraduate math curriculums that talk about nonlinear differential equations, if you can believe it. It's very simplistic. It's not adequate for people who need to do majors in physics and even in biology. Everything in your biology is disease modeling and all these things is related to this. So you have to understand the idea. But it's not very scary, is it?
No, just a lot. It's like go home and review.
But that's because you don't come to class. It's the first time I've seen you in weeks. Okay. All right. So you maybe lose my train of thought, but it's okay. I get it right. Okay. Any questions about this? So the main point is the following. Okay? Summary of what I just wrote. In nonlinear systems, either you can start with an initial state and uniquely tell me what the future will look like. Either you can start with an initial state and tell me uniquely what the previous state looks like. You can start with the final state and tell me what the initial state looks like. And if you're very fortunate, you can do both. But all of these possibilities exist when you're dealing with nonlinear equations. So that's a summary of what I wrote.
But at least one will apply.
At least one will apply. Must is. Okay. So, related to this is the following. And in fact, in many cases, when we'll talk about this in a bit, if I have some very well-behaved, it can be very deceiving too, because you can have some well-behaved system that when you evolve it into the future, just looks like a nice solution to a differential equation. If you try to evolve it backwards, you get very random, chaotic behavior. So it's very nonlinear as you try to go backwards. And there's very famous examples of this, as we'll see in weather prediction and other things like that. So this is a very important concept. Okay. So, related to the concept of flows is another thing. So, if F is once again C1 continuous, then not in terms of semi-flows, but just flows in general. So then phi of t, related to my dynamical system, consists of C1 max. What in the world does this mean? If you think about what does this mean? The flow, say it again, what is the significance of the flow?
So you have one totally time you see the behavior of all
All possible initial conditions. Anytime you see the word flow, guys, just take all possible initial conditions. So, if f is C1 continuous, then the flow of the corresponding differential equations consists of C1 maps. That means the flow themselves is C1 continuous. What does that mean? That means the flow. Solutions of the dynamical system depend smoothly on the initial condition. So, if your initial conditions are reasonable, your solutions are expected to be reasonable. In other words, you do not expect your solutions to behave all that different from your initial condition. And this theorem, much of differential equations could not be done if such a theorem did not exist. Yeah.
Okay, so in another lecture you're talking about like maps and like atlas system, atlas map. Is it similar?
No, the atlas was related to manifolds. So that you can generalize this in that area, but in this context, I mean map by function. I just mean, so C1 function. That was different, but so the solutions of your equations depend smoothly on the initial conditions you specify. So that's very important. Okay. So that's the basic theorems of differential equations. I'm not giving you proofs because Thomas is getting impatient. But I mean, you can look at the proofs. Okay. So I talked about the word orbit before, but let me expand on that. So orbits and the very important concept of invariant sets. So remind me, what is an orbit again? Roughly? Recall? I did mention it. I wrote it down. So an orbit is just the image of a solution of a differential equation. So when you draw it in your face portrait, we call that sketch an orbit. But formally, what is it? So definition. Given my dynamical system, once again, x prime equals f of x, and the corresponding flow, phi of t, the orbit through some point which I will just denote as x naught for lack of better words, which I will denote as gamma. So my orbit I denote by gamma, and the point it goes through is this x naught. Okay. Is defined as follows. So gamma of x naught is equal to the set x into Rn such that x is equal to phi of t of x. That's what you mean by orbit. So you evaluate the flow at your point. That's what you mean by orbit. Well, what does this mean? In other words, if you want to generate orbits of your system, you evaluate some points at the corresponding flow. That's what this is. And then, based on this definition, we can finally talk about the most important thing. So, the points in Rn, which is my phase space or state space, can be divided into two types of points. The first type are points you are already familiar with. Equilibrium point. And the second, if you do not have an equilibrium point of your system, you have what is just called an ordinary point. So I wrote this out for you before in the announcement for the test, but I will make it formal. So definition. What do you mean by equilibrium? I simply mean so-called. So, an equilibrium point, which I will call x0, of my dynamical system, x prime is equal to f of x, satisfies the following equation, namely, f of x0 is equal to 0. In other words, if you want to find the equilibrium points of your system, you simply set the right-hand side equal to 0, and those points such that f of the right-hand side is equal to 0 are your equilibrium, as you have been doing. So such points that satisfy f is equal to 0, we call them equilibrium points of the system. And now here's the thing. Okay? Equivalently, if you want to talk about flows, so I should mention this before. The flow is an important theoretical concept, but when you're actually doing computations, you never actually have to do anything with it, because you can't. The flow itself depends on knowing the solution of the differential equation. But with nonlinear systems, you often cannot write down the solution explicitly. So then you cannot write the flow down explicitly either. But I will always give you a flow interpretation in case people want to see the alternate view of it. So equivalently, even though this is more than enough for computational purposes, equivalently you can also say that the flow evaluated at x0 just gives you x0. So that's what you really mean by equilibrium. The flow is unchanged when it's applied to such an equilibrium. Okay. A little bit more. X, we called it an equilibrium point. Some people may even go as far to call it an equilibrium state of the system. And what does it mean if you have an equilibrium state of a system? Say it again? No, the state is not zero, but it's related to that. Think about it a little bit more. If I have a state of a system that's in equilibrium, it's in balance. And what is specialized about that?
It's stable.
It's stable for all time. Exactly. So equilibrium state is the same. In other words, the system does not change with time. So that's the significance of the equilibrium point. At that point, the system does not change. And in fact, you can see it. If f of x0 is equal to 0, that means x prime is going to be equal to 0. And if x prime is equal to 0, that means my system is not changing in time, because dx by dt is equal to 0. So related to this is the idea that dx by dt. In other words, my system, my state is not changing. So that's what you really mean by equilibrium. Question?
Yeah, I'm just wondering, could you have an equilibrium point where it wouldn't be stable?
Oh, yes. Yes, of course. You can have unstable equilibrium points, as you saw with your saddle. Saddle is not stable. It's half stable and not stable. Okay. So, an equilibrium point of the system, at that point the system does not change with respect to it. Okay. So, in other words, in terms of the flow, as I said before, the point x0 is unchanged when the flow acts upon it. In other words, it doesn't care. If you have an equilibrium point, it's just sitting there, it will always stay there. It doesn't matter if the flow acts on it. It doesn't care. It says, I don't care. I will continue to be in equilibrium. Okay. So I talked about the equilibrium. Is everybody clear on this? Okay. But then what does it mean to have an ordinary point? So if you don't have equilibrium points with this special property, then the only other possibility is if you have ordinary points. So let's talk about it. Okay. So there's two types. So let me actually state it. So in orbit, through an ordinary point, which is amusingly called an ordinary orbit. Is a smooth curve with f as tangent to that. Okay. And now you can have two types of ordinary orbits. So you know what an ordinary orbit is, you can have two types. Okay? The first type is the following. So let x0 be an ordinary point, which is not equilibrium, because it's ordinary. Okay. Then, gamma, which is my orbit, through x0, we say can be periodic. In other words, if you remember from your calculus course, what does it mean to have a periodic function? Even more general than sine and cosine. It just means that there's some t greater than 0, such that phi t, so the flow evaluated at that time, simply gives you the point. It's periodic. It keeps repeating. That's what you mean by periodic function, actually. So more general than sine and cosine, there's some point where if you apply the flow to it, you'll get that point back. Okay. Similarly, the other type of orbit is not periodic, but it's called recurrent. This is slightly different. So you'll start to see all these things in the examples that we do. But at least now you'll know why they are there. It's not just some computer magic. And the second case, as I said, is not the left. So let x not be, once again, an ordinary point with corresponding orbit gamma at x0, and we say the following. So assume that the orbit is not periodic. So if this is the case, then we say that gamma of x0 is recurrent. Means that for all neighborhoods call them, let's say, n of x0. So when I say neighborhood n of x0, I simply mean some region in the vicinity of x0. As I talked about before, and for all, let's say, time, there exists some other time scale such that y of t belongs to this neighborhood. So, in summary, if you want to think of it in terms of diagrams, it's a helpful way to recall these two types of orbits or describe these two types of orbits as the following. So in the periodic case, which is the first one, so periodic orbits, you get oscillatory behavior. Where the period of your oscillation is just t. And in the second case, the return case, which is very fascinating, actually. The system can return arbitrarily close to its initial state. So there's a lot of phenomena that occur in nonlinear systems which will not occur. Yes?
Does that mean it goes back to it? Because like
Almost goes back to it. So, if I was to expect, in my PDS course last year when I talked about classical mechanics, we spent 2 lectures on this point too. And the reason is that it's very fascinating what can occur. You can have some system, the only way it can return exactly to its initial state is if you let the system run for an infinite number of time. But you will, if such orbits occur in your system, it will frequently happen that no matter what the future evolution is, it will arbitrarily return to the initial state as well. So the common example is done in physics, where you have some thermodynamics, where you have some box, and you have a gas of particles. And what will happen is that you put a ball or a divider in this box. And after a very long amount of time, these particles will spread to the other side. Another example is if you have some, let's say, bowl, like this, and you place a marble or something at the top of this bowl and you let it roll down. Obviously, common sense says that this marble will continue to just oscillate around the bottom. But actually, you can show that there are many times where the marble will return back closer to the as you can actually imagine. So, you get a lot of weird things happening in nonlinear, which is very fascinating actually. Much of reality is nonlinear concept to me. So you can have very cool phenomena actually. And we'll see some of these examples in the things we do. Okay, any questions about it? So it's hard to appreciate this in a definition, but we'll see it. Question? Okay. So, here's another interesting thing that happens in nonlinear. So, when you guys solved on your exam, or did example questions with linear systems, how many equilibrium points did you always get? And what was that equilibrium point? Always 0. And if you're not convinced, you can always diagonalize your coefficient matrix to ensure that the equilibrium point you get is always 0. But in the nonlinear case, there's no such thing. So you can have many equilibrium points. Okay. As you'll see. So you just don't have one. As you can imagine, I said the only condition to get equilibrium points is f should be 0. But there could be many points where f is equal to 0. Hence, many equilibrium points in this. That all have different behaviors associated with them. Okay. So, a definition then. In orbit, connecting distinct equilibrium points we call a heteroclinic orbit. And you can also have orbits that connect equilibrium points to themselves. An orbit that connects equilibrium points to itself, to themselves, are what we call homophonic orbits. So that's the definition, and I'll just give you maybe a diagram to explain the complications of it. So the idea is something like this. So say I have some dynamical system, and I solve for its equilibrium point. And I get 4 of it. Let's just say 4. So call these, let's say, x1, x2, x3, x4. And in your phase space diagram, xy plane, let's say, you get something like this. So let this point be x1, let this be x2, let this be x3, let this be x4. So you solve for equilibrium points, you get 4 of them, let's just say, and you draw them out, and those are their coordinates. Each one of these, now it's a nonlinear system, can have different behaviors associated. So you can have something like this. You can have, let's just say, a heteroclinic orbit that joins x1 to x2. You can have one that connects x1 directly to x3. You can have one that connects x3 to x2. But then you see we also formed a homophonic orbit that connects x1 back to itself. You can have one that goes x1 to x4. Now here's the interesting question. In the linear systems case, it was clear when the point was a local sink or source, because all of the orbits would just go towards that. Now tell me, what is the local sink of this system? What is the source of this system? There's many of them. So, finding a sink and a source and a saddle are now local properties of the system, within some region of your phase space. So we have 2 questions now, next class, that we will start to answer. Is given many equilibrium points, what are the orbits? Are there any such orbits? What is the local behavior of each equilibrium point? So this is a sink locally, but most importantly, globally or asymptotically, what is this system evolving to? So if I let this system evolve for an infinite amount of time, what state will it settle into? Will it be x4? Will it be x1? Will it be x2? So there's ways to find it. So asymptotic behavior, very long time behavior, local behavior, we need to answer. Any questions on this? Oh, sorry, I wanted to go.
Thank you very much. Thanks. Appreciate it.